Stars are the fundamental building blocks of the universe, providing light, heat, and the conditions necessary for life. The process of star formation and evolution is one of the most fascinating aspects of astrophysics, involving complex physical and chemical transformations over millions to billions of years. We explore how stars are born, evolve, and ultimately meet their end, shaping the cosmos in the process. Stars form from vast clouds of gas and dust called nebulae. These regions, often referred to as stellar nurseries, are primarily composed of hydrogen, the most abundant element in the universe, along with helium and trace amounts of heavier elements. Gravitational collapse to star's formation begins when an external force, such as a shockwave from a nearby supernova or galactic collisions, disturbs a nebula. This triggers regions of higher density within the cloud, causing gravitational forces to pull matter inward. As the material condenses, it forms a protostar, an early-stage star surrounded by a spinning disk of dust and gas. Protostar development. As the protostar continues to accumulate mass, its core temperature rises due to gravitational compression. This phase can last hundreds of thousands to millions of years. The energy released from compression makes the protostar shine dimly in infrared wavelengths, but nuclear fusion has not yet begun. Onset of nuclear fusion. When the core temperature of the protostar reaches about 10 million Kelvin, K, hydrogen atoms begin to fuse into helium through nuclear fusion. This marks the birth of a main sequence star. The outward pressure generated by fusion counteracts the inward pull of gravity, achieving hydrostatic equilibrium. Once nuclear fusion begins, the star enters the main sequence phase, where it remains stable for most of its life. The energy from fusion creates the heat and light that stars emit. A star's position on the Hertzsprung-Russell (HR) diagram is determined by its mass. Low-mass stars, red dwarfs. These stars burn their fuel slowly and can last for tens to hundreds of billions of years. Medium-mass stars, like the Sun. These stars typically remain in the main sequence for 10 billion years before evolving. High-mass stars. Massive stars burn through their hydrogen fuel in just a few million years, leading to a more dramatic end. During this stage, stars continue fusing hydrogen into helium while maintaining a stable size and luminosity. As a star exhausts its hydrogen fuel, its core contracts while its outer layers expand, leading to different evolutionary paths based on the star's mass. For low and medium mass stars, Sun-like stars, red giant phase. Once hydrogen in the core is depleted, fusion slows, and gravity causes the core to contract. This heats the outer layers, causing them to expand. The star becomes a red giant, growing significantly in size. 2. Helium fusion begins, producing carbon and oxygen. Planetary nebula and white dwarf formation. The outer layers of the red giant are expelled, forming a planetary nebula. The remaining core, now a white dwarf, is extremely dense and gradually cools over billions of years, eventually becoming a black dwarf. Though the universe isn't old enough for any black dwarfs to exist yet. For high-mass stars, more than 8 times the Sun's mass, red supergiant phase. 1. High-mass stars evolve into red supergiants and continue fusion beyond helium, forming elements such as oxygen, silicon, and iron. Supernova explosion. Once iron accumulates in the core, fusion ceases because iron does not release energy when fused. Without outward pressure, gravity causes the core to collapse, leading to a supernova explosion, one of the most powerful events in the universe. The explosion disperses elements into space, enriching future star-forming regions. Neutron star or black hole formation. If the core left behind is between 1.4 and 3 times the Sun's mass, it collapses into a neutron star, an incredibly dense object composed of neutrons. If the core is greater than 3 times the Sun's mass, it collapses into a black hole, where gravity is so strong that nothing, not even light, can escape. Stars are not just celestial objects, they play a crucial role in the evolution of the universe. Element formation. Heavier elements like carbon, oxygen, and iron are forged inside stars through fusion and supernova explosions. Planetary system formation. The materials ejected by dying stars contribute to the formation of new planetary systems, including our own solar system. Galactic evolution. Supernovae influence the formation and structure of galaxies by redistributing matter and energy. The life cycle of a star, from its formation in a nebula to its eventual death, is a fundamental process that shapes the universe. Whether ending as a white dwarf, neutron star, or black hole, every star contributes to cosmic evolution. Understanding star formation and evolution provides insights into the origins of elements, planets, and life itself. As astrophysical research advances, we continue to uncover the mysteries of stars, deepening our knowledge of the cosmos.